Okay, this is the 2.1 graphing absolute value notes. The absolute value function is written as f of x equals absolute value of x. The table would show where you put -3 in, absolute value of -3 would be 3. So all of the values will be positive for y. Our function will look like a v. And the turning point, which is at 0, 0, is called the vertex. The domain is -infinity to infinity, and the range starts at 0 and goes to infinity. So it's 0 to infinity inclusive. So here's an example. It shows that we have a translation to the right of 4. If we set x minus 4 equal to 0, we do find out that x is 4 when y is 0. That's how the vertex moves over. So we simply move it from 0, 0 to 4, 0. If you put that in your center of your table, then you can count backwards 3, 2, 1, forwards 5, 6, 7, and then our y's basically stay the same as they are in our parent function. You go over 1, up 1. So we move over 1, we go up 1. So at 4, at 5, you're at 1. At 6, you're at 2. At 7, you're at 3. Our domain stays the same. It's still from -infinity to infinity. And our range also stays the same because we did not move anywhere from off the x-axis. So we start at 0 and go to infinity. The next question shows that we have a dilation going on. This is a horizontal dilation. So the best way to figure out where the vertex is going to land is to set 2x plus 6 equal to 0 and solve for x, where x is -3, then your y would be 0. And then because there is a dilation, it's also going to change our directions. So if you put -2 in, you get -2 times 2, which is -4, plus 6 is +2. Absolute value +2 is 2. And because this is a symmetric image, you can basically go from 0 to 2 and then 4, 4, 6, 6. What actually is happening is our y directions are being doubled because of that 2. And that gives us our image. Our domain and range stays the same because, again, we did not move off of the x-axis. So our range stayed from 0 to infinity, and we're still from -infinity to infinity for domain. So a quick overview of the terminology. The function is in the form of mx plus b, absolute value of mx plus b, because it is actually made up of 2 lines. From 0 to infinity is a y equals x line, and from -infinity to 0 on the domain is the y equals -x. So we can write it as in the form of a line. M cannot be 0, and m is the slope of the actual line, the direction. So that kind of helps you to figure out what it would be if you have an m, a number in front of the x. B is going to be your direction, that B would be your left, right, and then C is going to be your up, down on where your vertex will be. The line of symmetry is the line that crosses through wherever your vertex is. And it is in the form of x equals, in this case, 0. So we generally write the equation in the form of y equals a being a vertical stretch or compression times the absolute value of x minus h plus k, where h comma k gives you where your vertex is. It is the movement along the xy, or the x-axis, that's your h, and then along the y, which is your k. When your x is equal to h, that is where your x-intercept will be. So vertical translation is the same rules apply. Absolute value of x plus k will go up, minus k will go down. If the x minus h is inside the absolute value, then that means you're moving to the right. If you have plus h, it's moving to the left. Vertical stretches are where you are multiplying a whole number, 1 greater than 1 times the absolute value, and that changes your y's. It actually multiplies your parent function by how much a is. And the same thing with compression. It multiplies the parent function y's by the fraction, which causes compression. A vertical stretch will look like it's pulling up towards the ceiling. A compression will look like the it is actually flattening out the image. A reflection, if it's negative times the absolute value, that reflects across the y-axis, so it flips upside down. If it is inside the absolute value sign with the x, then it flips vertically, so it goes sideways. So a couple of examples. This one shows that we have x plus 2, which means that we're going to be shifting up by 2. And that means that our vertex just moves up by 2, but the actual image doesn't change its shape. So we still are going over 1, up 1, over 2, up 2, over 3, up 3. The range does change because our starting point actually moved up. The next question is talking about a shift both horizontally and vertically. So it went 2 to the right and 1 up, which changes our range to 1 to infinity, and our vertex becomes 1 to 1. But again, there's no change in size, so you can still do the over 1, up 1, over 2, up 2, over 3, up 3. So our next question is a vertical stretch. This happens when you have multiplied a whole number times on the outside of the absolute value sign. So we have not moved left or right or up or down because there's no translation. So our vertex stays the same. But what happens to our y value is interesting. Usually we go over 1, up 1, but when you do multiply by 2, it actually changes that y value to going up 2. So we go over 1, up 2, over 2, up 4, multiples of 2. A way to see that in writing is to do yourself a table where you're plugging in values of x that you would normally be moving, 0, 0 being the center. I go to 1, put 1 in, absolute value of 1 is 1, times 2 is 2, absolute value of 2 is 2, times 2 is 4. So that gives me my mirror image so I can figure it out. The same kind of thing applies here. We have a negative, which tells us that we're going to have an upside down negative f of x. And we can multiply our y values that we normally get by negative 2/3. I chose multiples of 3 for my x's because it's easier to multiply. 3 go into the absolute value, as absolute value of 3 is positive 3. 2/3 of 3 actually ends up being negative 2. Absolute value of 6, 2/3 of 6 ends up being negative 4. So we have our symmetry. Our next question has both a vertical and horizontal movement as well as a vertical stretch. So we're moving 1 to the right because it's -1, and we're moving 3 down because it's -3. And it is reflected, that gives us the negative. So we know we're going to have an upside down image. We're going to be at vertex of 1, negative 3. And then the stretch is going to multiply all my y directionals by 2. So I'm going to go over 1, down 2, over 1, down 2, over 2, down 4. So it doubles everything that we normally would have done. Okay, if we're writing an absolute value, I'm actually going to make a separate video for this part because it's a little bit more complicated. But basically you start with your vertex. So our vertex is at -1, positive 4, which means that we're going to have a +1 because we moved to the left, +1, and then we went up 4, +4. To get the a value, we actually have to choose a point on outside of the vertex. So I can choose 0, 2, and we plug them into what we already know. We know the +1, we know the +4, so we can put 0 in where x was, 2 in where y was, and then we can solve for a. And that gives us what our a value would be. And we know it should be negative because it was upside down. Same kind of concept here. We moved over to the right 1, so it's going to be a -1. We didn't go up or down, so we do not have a plus k. And then we'll pick one other point somewhere on the graph, which -3, 2 was an easy one. So we'll plug in -3 where x was, 2 where y was, and then we solve for a and find out that a is now 1/2. Okay, so our last example is comparing two functions. They are both absolute value functions, but one of them has a vertical stretch and the other one has a horizontal stretch. how we can tell the difference is a vertical stretch will be outside the absolute value sign and a horizontal stretch will be inside the absolute value sign. Also remember that 2 on the horizontal stretch actually tells us the slope of that line inside. So we can actually draw the 2x plus 1 as a line to where the vertex is, and it will give us an idea of what it would be. And the same thing going the other direction, we can actually draw the negative 2x plus 1 and it would give us the other direction. Another way of doing this is to make yourself a table. You would want to find out where your vertex is. Well, our vertex on the first one is going to be at -1, 0, because if I put -1 in there, that is going to give us 0. And then we can use our stepping going up several and down arrow several, and then also use that trick with the dilations. Since it's times 2 and it's a vertical, that's going to multiply all my directionals by 2. On the other one, we're going to have to set 2x plus 1 to equal to 0 to figure out where it is crossing at 0. And I do not have that one listed because I was trying to stick with the same numbers. So I put 0 in and I get it's at 1. I put 1 in, and 2 times 1 is 2 plus 1 is 3, so I get 3. And then it reflects. To get the actual vertex for this one, we would say 2x plus 1 equals 0, and then we'll solve for x. So that ended up being at x is -1/2, we're going to have our vertex. So that's why the vertex here on the blue one is at -1/2, and that's why the vertex on the other one is at -1. So they don't have the same vertex, and they also do not have exactly the same slope. Actually, the slope for this first one is a 1, and the slope for this one is a 2, so it's slightly different. Okay, the last page of your notes is some practice problems for you to do. This counts as part of your journal grade.